We're looking at question 4, matrix algebra. Consider the matrix A, which is equal to A, B, C, D. Part A is saying suppose M, a matrix M, multiplied by the vector X is equal to 1 minus 1. Calculate the determinant of A and the characteristic equation for an eigenvalue M of A and find the vector X. Cool, so determinant of A is just A multiplied by D minus B multiplied by C. The characteristic equation for an eigenvalue M would just be that A minus I is equal to 0. So we need to work out the determinant of the matrix A minus M, B, C, and then D minus M, and equate that to 0. So we will do A minus M multiplied by D minus M minus BC is equal to 0. So when we do this, we get M squared minus AM minus DM plus AD minus BC is equal to 0. So our characteristic equation is M squared minus A plus D M plus AD minus BC, which is going to be equal to 0. Now, to find the solution of xy, we simply have to find the inverse of M and multiply it by the vector 1 minus 1. And so the inverse of M is 1 over the determinant, and then brackets D minus B minus C A multiplied by 1 minus 1. And so we get D plus B and minus C minus A. So our solution is going to be D plus B all over AD minus BC and then minus A plus C all over AD minus BC. Cool. If alpha is a real number, then show by explicit calculation that det alpha M is equal to alpha squared times that of M, and comment on how you expect this result to change if M was an n times n matrix with n is greater than 2. Cool. So if we first work out the determinant of alpha times M, assuming M is just this matrix over here, we get alpha A, alpha B, alpha C, alpha D, and the determinant becomes alpha squared AD minus alpha squared BC, which we can write as alpha squared AD minus BC, which is just alpha squared and the determinant of M, because the determinant of M is AD minus BC. So hence we've shown that. And comment on how you expect this result to change if M was an n times n matrix. If we just quickly make a new matrix which is Z, and say that that matrix is a 3 by 3 matrix, so alpha A, alpha B, alpha C, alpha D, alpha E, alpha F. If we work out the determinant of this matrix, we have alpha cubed AEI plus alpha cubed BFG plus alpha cubed CDH minus alpha cubed GEC, alpha cubed HFA, alpha cubed IDB. So hopefully you can see that we can take out alpha squared and we're just going to get the determinant of Z. So what we can say is that if M is an n times n matrix, det of alpha M is equal to alpha to the power of n multiplied by det M. Cool. Should that det M multiplied by the identity matrix minus the trace multiplied by the matrix M plus M squared is equal to 0. So det M was AD minus BC, and then we have the identity matrix 1, 0, 0, 1. The trace is just the leading diagonal added together, so A plus D, and then the matrix M, which was A, B, C, D, and then plus A, B, C, D multiplied by itself. Cool. So if we expand out the determinant, we get this. If we expand this out, we get A squared plus AD, AB plus BD, and then AC plus CD, and AD plus D squared. And we're going to plus that with A squared plus BC, AB plus BD, AC plus DC, and then CB plus D squared. If we write this all as one large matrix, we're going to get this matrix. And as we can see over here, the A squareds cancel out, BC cancel out, and AD cancel out. So we get 0 over here. These two cancel, and then these two cancel. So we get another 0, and then these two cancel, and these two cancel. So we get 0, and finally these two cancel, these two cancel, and these two cancel. And so we get a 0 matrix. And we have shown that that is the case. Cool. Hopefully that all made sense.